Hey everybody, this is our video on balancing chemical equations, and by the end of this video you should be able to analyze the law of conservation of matter and how it applies to chemical equations. So first let's talk about what a chemical equation is and the different ways that we can see a chemical equation. So a chemical equation is just written as reactants going to products. Reactants are what start the equation, it's what you start with, what is being reacted or doing the reacting. Products obviously is what is produced. Each element that's on the same side, so like every element or compound that's on the reactant side, every element or compound that's on the product side, you have to separate with a plus sign. And then you separate reactants and products from each other using an arrow. So if you were to look at a statement and have to write an equation out of this, you look for the words yields, gives, reacts to form, produces. All of those mean arrow. So now that we know a little bit about a chemical equation, we could talk about word equations. And these are set up like an equation, except we use the names of things instead of formulas. So as you'll see in this example, if I give you the sentence, solid iron reacts with oxygen gas to produce solid iron 3 oxide, your word equation would be iron plus oxygen or oxygen gas, if you want to be specific, arrow iron 3 oxide. And then after we look at word equations, we look at skeleton equations. So this is where we start to pull in the chemical formulas. So if you struggled with naming and writing formulas of compounds, you may want to stop right here and go review from that unit to see those rules again. Because if you don't write it correctly, you can't balance. So we've got to make sure we're doing that. So this, again, the skeleton equation will show the formulas of the reactants and the formulas of the products, but not necessarily the amounts of each present. So for the example given earlier, we're going to write that out in a second. You are going to do it as you do. But there are certain things you have to recognize or make sure you do when you write these. First, write the correct formula. Next, you need to show the state of the substance. So an S is for solid, L is for liquid, G is for gas, and AQ is for aqueous, which means dissolved in water. So one thing to know here, look for the word solution. So if you see the word solution, that's a pretty much dead giveaway that you are dealing with something aqueous. And a lot of times I'll give you the state in the actual statement. So I said solid, iron, oxygen, gas. I'll tell you those things. But sometimes we could just make you assume the states of certain things. We know ionic compounds are solid at room temperature unless I use the word solution. We know what elements are normally in gaseous state, so just kind of keep that in mind. And then if you have a catalyst, so I say in the presence of this or in heat, things like that, you will write the catalyst above the arrow. A lot of times I'll just use heat as an example because heat is the one you'll see most of the time. You'll write the word heat, or you'll draw this triangle, which means a change. And usually it's a change in heat. So I don't have another example for you for this part because I gave you the word equation. Now I want you to take that word equation with the iron and oxygen, all that good stuff, and I want you to write the skeleton equation. A couple things to remember before you pause the video and try. Maybe. You must write the formulas correctly. Don't forget about diatomic elements, so those 7 that we know on the periodic table. Make sure you include the state of matter, and that's all you've got for that. So pause this video now and go try that example. So now we're looking at balancing equations. So once we have a skeleton equation written correctly, we can then look and try to figure out the amounts of substances in that equation. We balance equations because we must obey the law of conservation of mass, which says that matter is neither created nor destroyed. It can only change from one substance to another, one compound to another. And to make this happen, we have to look at the number of elements on each side. So you can't have an element pop up on one side of equation and not be on the other. So we have to count those up. To make them equal out or balance, we have to use coefficients. And coefficients are large whole numbers that go in the front of a compound. Since they go in the front, they are distributed onto each element in the compound, so it applies to the entire thing. If you stick a 2 out front, it applies to the first element and the second element. You never, ever, ever change the subscripts because remember, the subscripts are specific to the chemical formula. And just know when we put in coefficients, the only math we can do here is multiplying. So we do not add, we do not divide, we do not subtract. We only can multiply. So if we have an equation, we are looking at our steps to balance. So first is to count all of your atoms individually. So if you see in this GIF over here, we've got numbers written down starting out. I'm going to kind of let it clear out so you can see it. Here at this point, you will see that we have them listed out of how many elements are on each side. How many of each element is on each side. If you have a polyatomic that appears on both sides, keep it together. So if you see that you have an NO3 on the reactant side and an NO3 on the product side, you can calculate it as an NO3. You do not have to split it up. It makes life easier to do it that way. You start with the most complex compound, and then you use coefficients to balance the atom number on both sides. So when you're looking at this example over here, they start with the H3PO4 to balance the phosphoruses in P4O10, which is our most complex compound here. Oh, and then recount and repeat if you need to add in more subscripts. So we're going to try this one together, and we want to balance the following. So let me get my little pen out here. We're going to start by making what's called a T-table. We're going to split it into reactants and products. We have 3 different elements here. So as you can see, we have carbon present, we have hydrogen present, and we have oxygen present. So because we have those, we now need to count how many we have on each side. So and here we look at those little subscripts. So on the reactant side, I have 3 carbons. On the product side, I have 1. On the reactant side, I have 8 hydrogens. On the product side, I have 2. And on the reactant side, I have 2 oxygens. And on the product side, I have this one and I have these 2. So they're both oxygens. We're going to add them up. So we actually have 3. We're going to start with our most complex compound, which would be the C3H8. It's got the most stuff on it. And as you can tell here, we've got 3 carbons. We only have 1 on the other side. So let's just start by putting a 3 on that carbon dioxide. And that's going to give me 3 carbons because it goes on the carbon, but it also goes on the oxygen. I already have 2, so we're going to multiply those together. That gives me 6 plus the 1 we have here. So now I have 7 oxygens. Okay, leave oxygen to last because O2 is the simplest compound on here. So now we're going to move to hydrogens. I have 8 on the left. I only have 2 on the right. So let's stick a 4 out front here to get me to 8. Okay. And once we get to 8 there, remember it goes on each. So now we have 4 oxygens plus the 6 there. We now have 10 total oxygens. So now we have to go back to the other side. The only thing that's not balanced, so our carbons are balanced, our hydrogens are balanced, it's just our oxygens. We have 10 on the right. We only have 2 on the left. So we're going to put a 5 up there. And now we have balanced out the entire chemical formula. Okay. So pause the video very quickly and write that down. And then, again, pause the video and try this example.